This is an AIPMT question in rotational dynamics. Problem is like this. Point masses M1 and M2 are placed at the opposite ends of a rod of negligible mass. So, rod itself has no moment of inertia as its mass is negligible. Rod is set rotating about its axis as it is given for you. Position of the rod is given. Now, then work required to set the rotating rod is angular velocity minimum. So, we want angular velocity to be minimum. We want the work done required has to be minimum. Work done equal to, we have a formula half I omega square. So I has to be minimum so that the work done also will be minimum because omega naught is fixed. Angular velocity is fixed. What's the moment of inertia of that system I can calculate is I of the system is, this is the axis of rotation. So M1 distance from axis of rotation is x square. M2 distance from the axis of rotation is L minus x whole square. So this is M1 x square plus M2 of L square plus x square minus 2Lx or M1 x square plus M2 L square plus M2 x square minus 2M2 Lx. For work, that is change in rotational kinetic energy to be minimum, moment of inertia need to be minimum. If the moment of inertia need to be minimum, then di by dx has to be 0. When any function becomes 0, then moment of inertia has to become minimum is the respect to differentiation has to become 0. I know the d. Let's calculate di by dx. There is a formula, differentiation of x power n equal to n into x power n minus 1. So differentiation of x square equal to 2 into x power 2 minus 1. That is 2x. So m1 into differentiation of x square is 2x. m2 into differentiation of L square is constant because L is a constant. Plus m2 into differentiation of x square is 2x minus 2lm2 minus 2lm2 dx by dx, that is equal to 1. And for that has to minimum, for the work done to become minimum, differentiation with respect to x has to become 0. That implies 2m1x plus 2m2x, this minus on the other side becomes plus, equal to 2lm2. So 2 can be cancelled everywhere. X can be taken here, common m1 plus m2 equal to lm2. Implies x equal to lm2 by m1 plus m2. That's the answer for the problem. D is the answer for the problem. So what we need to know is, what shall be the position of the rod is the question. The position of the point P of this rod through which axis has to rotate. That means he can change this axis about which the system is rotating so that the work is minimum. For the work to be minimum, rotational kinetic energy to be minimum. Rotational kinetic energy, we have a formula half I omega square. But omega is omega naught fixed. So for the work to be minimum, moment of inertia need to be minimum. For the moment of inertia need to be minimum, its differentiation with respect to x, its location has to be chosen in such a way that at that particular location it will have a minimum moment of inertia. Mean to say, we have to choose x, this much of the value, this x, from this axis of rotation so that it will have a minimum work done or minimum energy. That's how we have to solve the problem. Thank you for watching.